All right, there's my dog Pebbles to say hello to you. She hates her picture taken. All right, so today we're going to do section 4.4, and if you watched the video I posted there of the 3 blue, 1 brown, that would help you with thinking about coordinate systems and like the visual of everything. So here we go. So if we spend a little time like making sure that in the beginning we know what everything means, it'll be a little easier for us later on. So here we go. So this first theorem 7, it says let B, so B is your basis, so I'm right here, all right, be a basis for your vector space. Then for each x in V, there exists a unique set of scalars such that to get x, you multiply all the things in your basis by those scalars. All right, so what this is saying, like in real people language, is this. It says, so if x is in the vector space V, then you know if it's in that vector space, then it is a linear combination of the vectors in the vector space. Because that's what it means to be in a vector in a vector space, is your linear combinations of the vectors that make up the space, like a linear combination of the vectors in the span. All right, and so that's all that thing is saying right there. All right, so this next little bit, let's highlight a little something here. So you have, again, a basis for a vector space V, and x is in V. So the coordinates of x relative to the basis are the weights that you give it, all right? And so that right there is going to have a special name. So the coordinates of x, you put a little bracket around it, relative to the basis. That's what that means. So this is going to be the weights, C1, C2, and all that. The weights applied to the things, the vectors in B, to make or to like get to x, right? Because you're going to have all this notation coming up, and it's good to kind of like know what it's talking about there. So that little piece, what it's talking about, what we just mentioned, was basically this. So this right here is xb. It's the weights that you apply to the basis vectors to make or go to the place that you want to go to, okay? All right, so let's look at this first example. So consider this basis right here. So we have our basis vectors. We have them right here and right here, all right? And we want to go somewhere. We want to go to x. And to do that, we have to apply these weights right here. So the way that you do that is you take -2 and you apply it to 1, 0. And then you take 3 and you move it or apply it to 1, 2. All right, and then you get your answer. So that's going to be where you're going. Well, if you notice, you can put this back into kind of like matrix multiplication. If you put the two columns, the two matrix columns together, 1, 0 and 1, 2. So see, if I would have done this up top, I would have gotten -2 times 1, so -2, plus 3 times 1, so 3. So I would have gotten -2 plus 3 is 1. On the bottom, I would have gotten 0 plus 6 is 6. All right, so I can also do that by putting -2, 3 back in its vector form and do this multiplication. I also get 1, 6. So this is going to be the format that we kind of go with because it's like the multiplication that we're used to. Oopsie, sorry. Ugh. All right, so then on example 1b, so they start talking about these basis vectors, all right, or their standard basis vectors. So this is, I don't know, like not super useful, but it's just kind of, it's a little bit confusing, but you know, your regular basis vectors are 1, 0. Remember, these are the columns of the identity matrix. This would be 0, 1, okay? So the entries in X, which we got above, 1 and 6, are the coordinates of x relative to the standard basis. So what they're saying right here is that 1, 6 is like what you do in the real world, and in this new world right here, where this is your basis vector, you do negative 2, 3, and you'll see a picture in a minute. So what we're going to try to do is just talk about that for a second. So what they're saying is that if you do 1 of the 1 zeros plus 6 of the 0 1s, you get 1, 6, which is pretty basic, right? So what we're also saying is that 1, 0 and 0, 1 times 1, 6 makes 1, 6. Okay? So the weights that we're trying to find, so when we find the weights in the standard basics, it's just the normal weights, like the 1, 6. So x relative to the standard basis is just 1, 6. So this looks the same as the original because it's the standard basis. Okay? All right. And remember what we found up here. This was x right there. Okay? All right. So on to the second page, and all these things will become more familiar to you as we do the examples. But I want to take you, remember this 1, 6 example, and that in this new world that we had right here, we were doing, this was our new world right there. So this new world is represented on the next page right here. So that new world was 1, 2 and 1, 0 were the basis vectors. So do you see how 1, 0 is that vector right there? And over 1 up 2 is this vector right here. So you have these new vectors. That's your basis. You have 1, 2, and you have 1, 0. Those are the things that make up your world. And on the video, that's like, you know, when he starts like moving around the graph and like squishing it and shrinking it and all that kind of stuff, but the origin stays in the same place. Well, this right here is our standard world, the 1, 0, 0, 1 world. Okay, so this is like our regular world, and this was our new world. So we're trying to see what to do in the new world to get the same place as we would in our regular world. So in the regular world, if I went to 1, 6, I would go over 1 and up 6, and it would put me right there. Okay. So in our new world, that thing, instead of going 1, 6, I should have gone negative 2, 3. So that means that I go back 2 of these ones right here. So I go back 2, and then I go up 3 of these 1, 2 vectors. So 1, 2, 3. And do you see, it's kind of weird because it's slanted, but do you see that if you look at the relationship between where the origin is and where you end up, it's a little bit, from the origin to the x, it's a little bit to the right and up. Well, that's the same thing as here to here. So x is in the same position relative to the origin. Okay, it's just telling somebody how to get there in the new world versus in the old world. Okay, all right, so you're really going to see this in 1C. It's in example 1C is just going to be everything kind of together here. All right, and so let's look at this problem. It says that you have a basis B1 and B2, and then you have your good old regular world basis 1, 0 and 0, 1. Okay, and XB is 2, 3. So remember, XB tells you the weights of what to do to your basis vectors. So it tells you what weights to use with these two things to get to the place that you're trying to go. So what you do is you take the basis vectors, you put them in a matrix as columns, you apply the weights to them, 2, 3. So this is your basis, this is your x, B, it's the weights of your basis vectors, and it's going to give you, so if you multiply that out, you get 3, 0 times 2, 3, so you get 6, and 1, 1 times 2, 3 gives you 5. So this gives you x. It gives you this place, like where to go, using this basis. So what this is telling you to do is telling you to go 2 of the first one, so 2 of these, and it's telling you to do 3 of these. Okay, so if I do that on my picture over here, it's telling me to do 2 of the 3 ones. So here it is, it's slanted because these bases right here, you know, over 3 up 1. So that's what's going on right there. That's the first vector in my basis. So it's telling me to do 2 of those, all right? And then it's telling me to do 3 of the 0, 1s. So 1, 2, 3. And so I've done that with the green and the red talking about down here, all right? So if I think back to my regular world, that should be regular world 6, 5. So if you go and do regular world, you have gone over 6 and up 5, all right? Because remember, this was 3, and over here you always went 3, 1, so you went over 3 up 1, over 3 more and up 1, so this is actually 6, 2. So do you see how it's 6, 5 now? All right. Okay, so if we want to see what's happening in our regular world, we would say to ourselves 1, 0, 0, 1. We would apply the 6, 5, and we would get 6, 5. So the regular world's kind of annoying or silly because we already know what that is. So x e, so using the standard basis. All right, so I wrote that kind of gross. So x with the standard basis, the weights that we would use would be 6, 5. Okay. All right, so we're basically kind of done. The rest of them are just kind of like, well, actually, no, we're probably like 2/3 of the way. We just have to go backwards a little bit. All right, so in example 2a. So example 2a, they gave me the basis, but this time they gave me the x. They gave me the answer. They didn't tell me the weights to use. So what they gave me here is 2, 1, and negative 1, 1. They gave me my basis. They didn't give me the weights to use. So they didn't give me the C1 and the C2 to use. They didn't give me x, b. They didn't give me the weights to use on my basis. But they did give me the answer 4, 5, like where they want me to go. All right, so you can solve this like any way you want. You can use the inverse. You can set it up with RF. So just make a note to yourself, inverse, or you can do RF. Right? But 2 by 2 is not too hard to find the inverse of. So you can go ahead and do that by 1 over the determinant. So the determinant of my matrix right here is 2 minus negative 1, so that would be 3, right? So I have 1 over 3, and then remember you switch around. So you switch the 2 and the 1 in the corner, so that's 1 and 2, and then you make the other one's opposite, so this would be positive 1 and negative 1. So my inverse of my basis is 1/3, 1/3, negative 1/3, and 2/3. Okay, all right. So when you solve that, and if you multiply this by 4, 5, so my xb right here, my C1 and my C2, is going to be the inverse of this matrix. So 2, negative 1, 1, 1, inverse times 4, 5. All right, so if I multiply this guy over here by 4, 5, I have 1/3 times 4, so that's 4/3, and then I have 1/3 times 5, so that's 5/3. Well, 4/3 and 5/3 is 9/3, so that's 3. Okay, so I get 3. And then if you do it with the bottom row, you end up getting 2. All right, so let's make sure what we just found right here. This that we just found right here was x, b. They were the weights to use on the basis vectors to get x. Okay, so remember this was x right here. All right, so down here, some little just rules right here. This part right here is what we were doing in example 1. And what we just did in example 2 was that part in green. Okay, so PB negative, so basically what they're saying here, this is going to be called P of B, all right? And what we just found over here, this was PB -1, right? All right, and we did that process. So the last couple of pieces right here, we're just gonna do that again. And let's see. So example 2b. So we have our basis vectors and we have x. So it's kind of like the same situation we had example 2a. So we just want to basically know what we're finding right now and do all that. So I have basically been given 3, 1, 0, 1 times xb. I don't know what the weights are, but it comes out to 6, 8. Okay, so I need to find the inverse of this guy. So right now I know that P of b is 3, 1, 0, 1. I know x is 6, 8. All right, I need to find xb and also p, b, -1. All right, so when I do this, I will have x sub b. When I get my inverse, so let's find the inverse of this thing real quick. I have 3 minus 0, so I do 1 over 3. And then if I switch everything around, this would be a 1 and a 3. This would be 0 still. This would be -1. So my inverse right there is 1/3, -1/3, 0, and 1. So that is my inverse of my transfer or my change of coordinates matrix. Okay, this guy right here. All right, so that will be 1/3, 0, -1/3, and 1. All right, and so if I multiply that by the 6, 8, that will produce an answer of 2 and 6. And this guy right here, remember, that is xb. So those are the weights to apply to my basis to get to the place that I want to get to, which is 6, 8. All right, that's ugly. Let me just fix it. Okay. All right. So these last two little problems, and there's your homework down there, just those 4 problems. So this time it's going back to what we were doing on the first page. So they've given me the basis vectors. They give me the weights. This xb is the weights. So remember, I have pb times xb equals x. All right, so they've given me these 2 pieces this time and want me to find x. So all I have to do is put 4, 5 and 6, 7 times 8, -5, which gives me x. So this comes out to 2, 5. So 2, 5 is the place I'm gonna go if I go 8 of these and 5 of those, -5 of those. All right, and down example 4 is just giving us basically the opposite. So I have my basis vectors, so I put that in my matrix, 1, -2, 5, -6. I don't know the weights. I don't know xb. And I'm going to get to 4, 0. So 4, 0 is like what you do in the normal world, and xb is you want to figure out what to do in this new world to get to the same place you would in the old world as going 4, 0. So basically we're asking, how do I get to here in the new world? Okay. All right. So you would figure out your inverse and solve this. So xb, oops, would be, oh God, that's just so ugly. xb would be the inverse of this PB matrix. Remember, this is PB. 1, 5, -2, -6 times 4, 0. All right, and so you've seen us find the inverse a whole bunch of times, and so when you do that, I'll write it over here on the side in a minute, but you get -6, 2 when you actually do that, or you can just use your calculator. So when you do your inverse, the determinant is 4, so 1 over 4. You switch everything around, so this becomes -6, and this becomes 1, this becomes -5, and then 2. Okay, so you can see your inverse is -3/2, -5/4, and 1/2, and 1/4. So there is PB -1. Okay, and so that's what I was multiplying by 4, 0 to get my xb. All right, and there you go. And like I said, you got those 4 problems for homework, and I will